All right, finishing up section 2.2 here. We've already started talking about concavity. Remember, when a graph is concave up, it's got a curve kind of like that. And when a graph is concave up, it has increasing rates of change. So a graph being concave down is going to look something like that. And that is when your graph has decreasing rates of change. So if you can find rates of change of two different intervals, if they're getting bigger, your graph is concave up. If they're getting smaller, your graph is concave down. A point of inflection will occur when a function changes from concave up to concave down, or from concave down to concave up. At a point of inflection, the rate of change of a function changes from increasing to decreasing or decreasing to increasing. You have to switch at that point of inflection. So looking at this graph, we're going to find any values where g has a point of inflection. So anywhere that we switch from concave up to concave down. Well, it looks to me like we switch about here and about here. The graph is concave up until we hit -1, then it's concave down until we hit 1, then the graph is concave up again. So I would say our points of inflection are about -1 and +1. Then we're going to look at each interval here and determine if its rate of change is increasing or decreasing, and why. So for our first interval, 3 to 4. So from 3 to 4, is my rate of change increasing or decreasing? Well, my graph is concave up, which means the rate of change is increasing. And our reasoning can be because it's concave up. There we go. From -4 to -3, our graph was also concave up, so that means our rate of change is increasing. Again, because it's concave up. From -1 to +1, our graph was concave down, so that means our rate of change is decreasing. Because our graph is concave down, we knew that. And from 1 to 2, my graph is concave up again, which means our rate of change is increasing since it is concave up. So concave up tells me that the rate of change is increasing. Concave down tells me the rate of change is decreasing. And now an important theorem, the intermediate value theorem. Let f be a polynomial function if a is less than b, so we're going left to right. If f of a and f of b have opposite signs, so one's positive and one's negative, then f has at least one 0 in the interval, a to b. Basically it says the function has to take on every value between f of a and f of b in between a and b. So how does this help? Between any two zeros, there must be a relative maximum or a relative minimum. So we're going to show that this function has a 0 on the interval -4 to -3. And to do that, it's quite simple. We just need to find f of -4 and f of -3. So to find f of -4, I just plug in -4 for all my x's. And when I plug that in, I get -9. Then I plug in -3 for all my x's. And when I plug that in, I get 12. Well, since f of -4 is less than 0, and f of -3 is greater than 0, we must hit 0 somewhere between -4 and -3. So there must be a 0 on the interval -4 to -3. Since one side is smaller, one side is bigger, we have to cross the x-axis. Now we are going to sketch the graph really quick of f of x equals 3x to the 4th minus 4x cubed. To do this, we're going to start with the end behavior. The degree is 4. The leading coefficient is 3, which is a positive, which means both our ends go up. The limit as x approaches -infinity of f of x equals infinity, and the limit as x approaches positive infinity of f of x is also infinity. So there's our end behavior. Then we're going to look at our zeros. And to get our zeros, I'm going to factor out an x cubed, which leaves me 3x minus 4. My zeros are x equals 0 and x equals 4/3. Well, let's see. X equals 0 has a multiplicity of 3, which means we cross the x-axis at that point. 4/3 has a multiplicity of 1, which means we also cross the x-axis at that point. I can make my little sign chart down here. I've got 0 and I've got 4/3. If I plug in something less than 0, let's say -1, I get a negative times a negative makes a positive. If I plug in something between 0 and 4/3, let's say 1, I get a positive and a negative, which makes a negative. Something bigger than 4/3, let's say 2, I get a positive, positive. There we go. So on my graph, I know I need to cross at 0 and 4/3. 0, 0, 4/3 is about there. I know my graph is positive, crosses through the x-axis, and then crosses through again at 4/3. There is my nice sketch. And one final piece of this section, determining the degree of a polynomial given a table of values. If given a table of values with equal length input intervals, this is very important. It means that the x's are always the same width apart. We're not jumping. Sometimes it's 1 apart, sometimes it's 3 apart. The x's will go in even intervals. We can determine the degree of a polynomial by examining successive differences in the output values. The number of successive differences needed for the differences to be constant is equal to the degree n of the polynomial. Let's look at how that works. So I've got a table of values. First off, my x's have to be the same distance apart. We're going by 2's on my x's, so this process will work. I like to just extend my table. I don't know how many more columns I'm going to need. Just give myself enough space. Make myself a column for the first differences. Well, we'll never have one at the top. So now I take -3 minus -2. That gives me -1. I take -1 minus -3. That gives me 2. 4 minus -1 is 5. 12 minus 4 is 8. Those are not the same number. This polynomial does not have a degree of 1. So then I do my second differences. Well, if I didn't have a first difference there, I can't have it. There's nothing to compare here, so I now have 2 boxes with x's. 2 minus -1 is 3. 5 minus 2 is 3. 8 minus 5 is 3. Those are all the same number. My second differences are a constant. That means the degree of this polynomial is 2. Second differences, degree is 2. Let's try it on another one. Extend my table a little bit. All right, for my first differences, well, first, are my x's the same distance apart? They're going by 3's, we're good. All right, I won't have a first box. 0 minus -2 is 2. 10 minus 0 is 10. 27 minus 10 is 17. 50 minus 27 is 23. Okay, it's definitely not a first degree. Try my second differences. Now I have 2 missing boxes. 10 minus 2 is 8. 17 minus 10 is 7. 23 minus 17 is 6. Those aren't the same number. It's not a second degree polynomial. Try my third. I have 3 empty boxes. 7 minus 8 is -1. 6 minus 7 is -1. Those are the same number. The degree of this polynomial is 3.